will speak about an operator-theoretic approach to nonamenable percolation.
Thank you, Nina, and thanks everyone for coming. So I'm going to be talking about percolation, so let me just start by very quickly going through the absolute basics of percolation. So we take some graph, and for me in this talk, the graph is always going to be connected. It's always going to be locally finite, which just means that every vertex has finitely many edges coming out of it, and it's always going to be transitive as well, which just means that for any two vertices u and v, I can find an automorphism of the graph, a symmetry of the graph sending u to v. So that just means that every vertex looks the same. Okay, so we take this graph and we're doing percolation on it. So for each edge, we have some probability p, we flip a coin. If the coin comes up heads with probability p, we keep the edge or say it's open, otherwise it's closed and we delete the edge. Okay, so that's percolation. And you know, the thing that makes percolation sort of an interesting model, so the first thing that you learn about percolation is that typically there is a non-trivial phase transition. And in fact, it's actually known now due to recent work of, well, there's 5 authors on the paper, so I won't listen, but not me, that this is actually true, that one-dimensional graphs are the only examples of transitive graphs that don't have phase transitions for percolation. Okay, and so we have this critical probability PC. So below PC there are no infinite clusters. Above PC there are infinite clusters. Okay, so what are the most basic questions about percolation we can ask? Well, first of all, the first big question is, what is the nature of this phase transition? So we know that it occurs, but what more can we say about it? So for example, do we have an infinite cluster at criticality or not? And you know, if we can, typically we expect that there is not an infinite cluster at criticality, and then once we know that, we'd like to go further. We'd like to describe various critical exponents. You know, what's the probability of having a big cluster at criticality, that kind of thing. Okay? And then a second very basic question is, well, I know that above PC I have infinite clusters, so I can ask, well, how many of them do I have? Do I have just one infinite cluster, or do I have 5 or infinitely many? You know, what are the possibilities there? Okay, so looking further at this second question, it's natural to define a second critical parameter, which we call the uniqueness threshold, Pu. So Pu is going to be the smallest p, such that for the infemal p, such that for some p above this, we have a unique infinite cluster. Okay, and well, some basic things about this are known. So first of all, Newman and Shulman showed back in 1981 that you cannot have 5 clusters. You have to have 0, 1, or infinitely many. So so really, in this uniqueness, non-uniqueness, we're really just separating the uniqueness from infinitely many. Okay, and then if we're looking at these questions on hypercubic lattices, ZD, which is of course the classical situation we were looking at, then it's been known again since the 80s that you cannot have infinitely many clusters. This was first proven by Eisenman, Keston, and Newman, and then there was a very short proof a few years later by Burton and Keen. So they showed that on hypercubic lattices you cannot have infinitely many infinite clusters. So this PC is equal to Pu in particular. Okay, and then just another very nice thing to know is that, well, you might say perhaps this Pu thing is not really the right thing to look at, because there's sort of no monotonicity in this thing about having a unique infinite cluster. You know, maybe for some p I have a unique cluster, and then I raise p a bit, and some new cluster is born that's separate from the existing one, right? So it might be that you sort of oscillate between the two behaviors, and that defining Pu and thinking of this as these 3 phases is not the right picture. But fortunately, it was proven back in the 90s in a series of papers by Hagstrom, Perez, and Schonman that if you're above Pu, then you really do have an infinite cluster, so a unique infinite cluster. So you can't oscillate between uniqueness and non-uniqueness. And this is not at all obvious. Okay. So one really nice thing about this Burton-Keen argument for uniqueness in ZD is it's really, really general. So it's not that specific to Bernoulli percolation. You can do it for all kinds of dependent models. And it's also not very specific to ZD. So in particular, it actually generalizes to all amenable transitive graphs. Okay? So what this means, what does amenable mean? Well, suppose I have my graph, and I define its Cheeger constant, hg, as follows. I look at all finite sets of vertices in the graph, and I look at the ratio of the number of edges in the boundary of the set, i.e. that have one endpoint in the set, one endpoint outside the set, divided by the number of edges that have both endpoints in the set. Okay, and I take the infimum over all finite sets of vertices. And I say the graph is non-amenable if it's positive, and amenable if it's 0. Right? And just as a very simple example, if I take the square grid, or a hypercubic lattice in any dimension, if I take a big box, then the denominator here is basically the volume of the box. It's going to grow like n to the d, if I have a box with side length n, but the numerator is just the size of the boundary, so it'll grow like n to the d minus 1. So if I take a really big box, I see that this goes to 0, so ZD is amenable. On the other hand, if I take a 3-regular tree, as pictured on the right, it's not too hard to see. You can do it as a computation with Euler's formula, if you like, that it's non-amenable. If I take any finite subset of this infinite 3-regular tree, then a constant proportion of the vertices have to be in its boundary, right? So it's non-amenable. Okay. So as I just said, the Burton-Keane argument really shows that for all amenable graphs, you cannot have a non-uniqueness phase. And Benjamini and Schramm in 1996 conjectured that the converse is also true. So they conjectured that if you have any non-amenable transitive graph, then PC is smaller than PU. So you really have a phase in which there are infinitely many infinite clusters. Okay. So it's very easy to see this on the tree because it's very easy to see that PU is 1. So, and you can compute PC to be 1 over the degree minus 1. It's just a branching process argument. So for a tree, this is very easy to see that you really have, in the tree, you don't have a uniqueness phase. You only have a non-uniqueness phase. If you look at something like a tessellation of the hyperbolic plane, then in fact you have all 3 phases. This was proven by Benjamini and Schramm. So you have, 0 is less than PC is less than PU is less than 1. You really get all 3 phases in this example. And it's not as easy as for this, but you can imagine that in a planar context, you have duality arguments that are extremely helpful for establishing this kind of thing. Okay. So if we're thinking about this PC versus PU problem, well, the thing about percolation is really, PC versus PU, it's a problem about what happens when you're slightly above criticality. But really, the only way we know how to do anything with percolation is to approach PC from below and try and get information out of it that way. So this, the problem of PC less than PU is very closely related to understanding really what happens at criticality. So luckily, the most basic thing we can ask about critical percolation is well understood in this context of non-amenable graphs. So the first big breakthrough here was by Benjamini, Lyons, Perez, and Schramm in 1999. So they showed that if you have a non-amenable transitive graph and it has this extra technical property called unimodularity, but this holds, for example, for Cayley graphs of groups, then they showed that, that you do not have any infinite clusters at PC. And then this unimodularity thing has been, it's no longer necessary for the theorem. Now we have it for all transitive non-amenable graphs. And so for the reason for this is that Adam Timar proved that in this non-unimodular case, he proved that you can't have infinitely many infinite clusters. You have at most 1. And then a couple of years ago, I had a paper showing that if you just have exponential growth of your graph, which is a weaker condition than non-amenability, for example, it holds for lamplighter groups and things like that, which have exponential volume growth but aren't non-amenable, then you can't have a unique infinite cluster at PC. That's what I showed. So if you take all these things together, you find that in any transitive graph of exponential volume growth, there cannot be an infinite cluster at PC. And since exponential volume growth is a weaker property than non-amenability, we completely understand this theta PC equals 0 problem in this case. Okay. So knowing that there's no percolation at PC is great, of course, but to understand PC versus PU, we really need much more quantitative, strong information. So really what we'd like to show, and this is sort of a separate conjecture, but separate but related, is that on any non-amenable graph, critical percolation has mean field exponents. So essentially what this means is, what we imagine is that if we have a sufficiently high-dimensional graph, then critical percolation on the graph looks a lot like a critical branching random walk on the graph. You know, somehow percolation is quite like branching random walk, but with some sort of interaction, because, you know, it meets itself and then it gets complicated. But in sort of a sufficiently high-dimensional setting, these self-interactions should be sort of irrelevant, and it should just behave like critical branching random walk. So there was a very nice sufficient condition for this behavior that was introduced by Eisenman and Newman. It's called the triangle condition. So if I define this tau p x y, that's just defined to be the probability that x and y are connected in percolation with probability p. And we also call this the two-point function. So the triangle condition just says I fix some vertex x, and I sum over all y and z of this triangle diagram. So the probability x is connected to y is connected to z, and z is connected to x. Although note that it's not really the probability that all those connections occur, it's the product of the two-point probabilities. Okay? So Eisenman and Newman, and then various other works building upon them later, showed that if you have this sum is still finite at PC, then you can make this comparison to critical branching random walk rigorous. So, for example, if you look at the probability that the cluster of the origin in critical percolation has volume at least n, it's going to grow like 1 over root n, right? Which is the same asymptotics as just taking a critical branching process and saying what's the probability it has total progeny at least n. Okay, but there are many exponents for percolation that can be derived once you have this triangle condition. Okay, and you know, if I mention the triangle condition, I have to mention that this has been proven to hold in high-dimensional lattices by Hara and Slade in probably one of the most famous papers in percolation. And now, you know, they did it for D at least 19, and this has been pushed down and refined by Remco van der Hofstad and Fitzner to D greater than or equal to 11. But basically, we expect in ZD that this holds strictly above 6 dimensions. And below, it shouldn't hold, and you should have different exponents. Okay? But if we're interested in non-amenable graphs, these are really, really high dimensional. I mean, they're infinite dimensional. So we should have much, much stronger assumptions than we really need to establish this. So we really strongly believe that the triangle condition should hold in the non-amenable case. Okay, so let's just mark that down as a conjecture. So as I said, really, just volume growth bigger than 7-dimensional should be sufficient for this to be true. So non-amenability should be massive overkill. But we still are very far away from having any idea how to prove this in general. Okay. So let me tell you about some sort of old results on these two problems, the PC less than PU and the triangle condition. So the first paper that was seriously looking at percolation on a non-trivial, non-amenable graph specifically was this paper by Grimmett and Newman in 1990. So they looked at, you take a k-regular tree and you take a product of that with a hypercubic lattice. And they showed that in this example, if you take the tree to have high degree, then you can find that there are these, you have all three phases, the non-existence, the non-uniqueness, and the uniqueness. Okay? And similar sort of ideas have been used by various people to establish perturbative criteria under which these things hold. So the idea is, we want these to be true for all non-amenable graphs, but if we replace non-amenability with a stronger quantitative assumption, for example, that the Cheeger constant is not just positive, but it's large, or various other things like that, then it's actually quite easy to establish these things via combinatorial arguments. You know, you just directly compare percolation to branching random walk, and if these constants are favorable enough, you can just do this quite easily. Okay, so in particular, one thing that was done this way is Pak and Smirnova Nagnabeda proved that if you have any non-amenable group, then you can find some generating set so that the Cayley graph will have these things be true. So this is really nice, but on the other hand, these methods sort of clearly aren't going to give the general conjecture. They're really very specific to this case where the constants are massively in your favor and you can just sort of brute force it. Okay. So what about non-perturbative arguments? So the first thing people looked at that's very natural is the planar case. So as I said, you have duality there. So think about these tessellations of the hyperbolic lattice. So for these things, it was proven that PC is less than PU back in the late 90s, early 2000s. And then there was a sort of a generalization of this. The condition here is a bit complicated. It's this cost greater than 1. It's a funny ergodic theory condition on the groups. But the main example here is that suppose I took one of these planar hyperbolic lattices and I made it not planar. I connected everything within distance 5. So these arguments wouldn't work, but this thing still does. So for any sort of thing that smells like the hyperbolic plane, these two results are going to get you what you want. Okay, but in particular, they don't apply to sort of lattices in higher dimensional hyperbolic spaces. Okay, and then, so it actually was still open to prove the triangle condition for these guys, but Schoenmann proved that for planar, for tessellations of the hyperbolic plane, you can get a lot of the mean field critical exponents just directly. He did it without going through the triangle condition. Okay, and then just say that until the recent work I'm going to describe, I think the only completely non-perturbative proof of the triangle condition in a non-trivial example was due to Gadi Kozma, who looked at the product of two three-regular trees. Okay, so the new results that I have to talk to you about today, and I'm mostly going to talk about the second one. So the first result is that a condition for both of these things to hold, and it's a symmetry condition on the graph. So what the result says is that if I have my transitive graph, if it has what's called a transitive non-unimodular subgroup of automorphisms, okay, so I'm not going to tell you what this means, then you get these conjectures are true. So basically the main example here is you take a product of a tree with something else. So in particular, this lets you complete the program that Grimmett and Newman started looking at the tree times ZD, and you don't need the tree to have large degree. It's all non-perturbative analysis. Okay, and the second thing that I want to tell you more about is the Gromov hyperbolic graphs. So if you introduce this extra hypothesis as well as being non-amenable, that it also has this geometric condition of being Gromov hyperbolic. So here you should think about a lattice in hyperbolic space. Then you get these two conjectures are true. And again, this was known in 2 dimensions, but not in higher dimensions before. Okay, so so the main thing I want to talk about for the rest of the talk is not quite about the proof of these theorems, but about some of the ideas, some of the new ideas that go into them, and mostly some of the easy parts of the new ideas that go into them. So one of the main ideas in the hyperbolic proof is to look at this sort of operator-theoretic perspective on percolation. So let me just remind you. So I'm going to have my graph still, and I have the vertex set, and I'm going to look at non-negative matrices indexed by the vertices, and they'll all be in 0 infinity, which is just nice because then I can always add matrices and multiply them, and it's always well defined. Okay, and I can define their operator norm from P to Q to just be, the norm of the matrix if I think about it as an operator from LP to LQ on the vertex set. Okay? So what I'm going to do is I'm going to look at the matrix of connection probabilities. So I'm just changing the tau to a T, basically, but that signifies that I'm thinking of it as a matrix. Okay? And so I can define a family of new critical values, PQQ, to be the supremal value of P, such that this operator norm is finite. And this turns out to be a really, it's sort of a basic thing to do, but it's a really nice thing to do, and it was something that was, I think, sort of missing from this literature before. So the new conjecture that I introduce, and that I want to tell you more about, is that PC, for any non-amenable transitive graph, PC is less than P22. So in particular, at criticality, this matrix of connection probabilities should still be bounded as an operator from L2 to L2. Okay, so why is this a nice conjecture? Maybe we can talk about why it's a reasonable conjecture afterwards, but let's talk about why it's a nice conjecture for now. So, first of all, it's clearly stronger than the PC less than PU conjecture, because if I'm above PU, then I can always bound the connection probability by the product of the probabilities that both vertices are in the infinite cluster. So if I'm above PU, these matrix elements are all bounded below. So if I'm in an infinite graph and I have all the matrix elements bounded below, I clearly have infinite norm, right? So I immediately get that PU is at least P22. So the conjecture implies the Benjamin-Isham conjecture. But it also implies that the triangle condition is finite. And that's because, well, this triangle sum, I just take this matrix, I take its cube, and I evaluated it on the diagonal, right? That's exactly the same as this triangle sum I wrote down before. So in particular, if the matrix evaluated at the diagonal is at most the norm, so if I have that the norm is finite at PC, then I immediately get that the triangle condition is finite. Okay, and in fact, you can even prove that this new thing P2 to 2 is exactly the same as if I take the largest P where the triangle condition holds. But this is sort of just an aside. But the really nice thing about this is, as well as implying these things that we'd like to prove, it also gives us a really nice thing to aim for. You know, it's one of these things where having the right strengthening of what you want to prove makes it that much easier to prove it. Right. So it really gives us what the estimate we want to prove about critical percolation is, if we want to then say something about slightly supercritical percolation. We want to come at PC from below and prove that the operator norm is not diverging. Okay. And another really nice thing is it actually has a bunch of very strong consequences that are not known to follow from these two things alone. Okay. And I should say at this point that these two theorems that I mentioned before, in both of these cases, I in fact proved the stronger thing that PC is less than P22. And moreover, the perturbative criteria for non-uniqueness and the triangle condition that I mentioned before, they also always yield this stronger thing. So it's a very reasonable, basically the only setting where we don't know how to prove it but do know PC less than PU is this cost thing. Okay. So one of the really nice things about these operator norms is that, so classically in percolation on ZD, what we do a lot of the time is we analyze the susceptibility. So that's just the expected size of the cluster at the origin. And it turns out that many of the techniques that people use to analyze the susceptibility, so you want to get various sort of differential inequalities for it and so on, they actually work for these operator norms as well. So you have this quantity that behaves a lot like the susceptibility, but potentially has a different critical parameter associated to it. And one reason that these things behave so much like the susceptibility is that if Q is 1 or infinity, then it just is the susceptibility. And that just follows from elementary facts about these matrix norms, that the 1-to-1 norm is just the maximum column sum and the infinity to infinity norm is the maximum row sum, so this very easily yields this fact that the norms are the same as the susceptibility. Okay. So one of the most classical results about the susceptibility is what's known as the sharpness of the phase transition. So this was proven by Eisman and Barsky, and in ZD also by Menshikov, but the Menshikov proof doesn't work in the general transitive setting. So what they showed is that for every subcritical P, the susceptibility is finite, right? So below PC, you know, the cluster at the origin is is finite almost surely, but they showed that it also has finite mean volume. Okay? And also what they get is that as you approach PC from below, the susceptibility has to diverge at least like 1 over PC minus P. Okay? And in particular, this means that these new critical parameters we introduce, if we set Q to be 1 or infinity, it's just the same as PC. Okay. So it turns out that this argument giving this divergence, this stability, works exactly the same way for the operator norms. So if I take the operator norm of my matrix and I'm at P, which is below PQQ, then it has to diverge at least like 1 over PQQ minus P. And this is really useful because in our setting we want to show that PC is less than P22. So really what we want to do is we want to show that the operator norm, the 2 to 2 operator norm, is finite at PC. But this says I don't really need to prove that. I just need to show that it's not blowing up too fast, right? So I get this huge amount of extra room to play around with. So to prove the boundedness, I really need to prove something strictly weaker, and this is really helpful. Okay? And actually, the way you prove this is very simple. So the way it works is you do the following. So imagine P2 is bigger than P1, right? Then what you can write down is the following inequality. So I'll write this squiggly inequality to mean entry-wise comparison of matrices. Right? And what I get is that TP2, I can bound it entry-wise by the following infinite sum. So I take P2 minus P1 times the matrix times the adjacency matrix of the graph that just says which vertices are adjacent to each other. I take this whole thing to the k and I multiply by the matrix again. Okay, and the reason this inequality is true, it's just an exploration argument. So, you know, I first, sorry, these should be P1s. Okay, so what I do is I first reveal the P1 cluster of the origin, right? And then there's going to be some edges that open up when I go from P1 to P2. Right? So, you know, I look at these sort of blue edges coming out that open up, and then I keep exploring my P2 cluster this way. So for each of these P2 edges that opened up, I can, you know, explore the P1 cluster and so on. And obviously, you know, these things are sort of interacting. I mean, this new P1 cluster I find can't re-enter the cluster that I already explored. But if I ignore that interaction, I get an upper bound, because this is sort of, it's only hurting my connection probabilities, the interaction. And you can make this precise, for example, with the BK inequality. And if you do this, you exactly get this inequality here. So each term in the sum corresponds to one generation of doing these explorations where I've done sort of, I've explored k of these edges which are open at P2 but not P1. Okay? And if you just take norms in this inequality, you very easily get this, because what will happen is if I'm only epsilon away from this point where the norm is supposed to be infinite for all larger p, right? I'd get a contradiction if this wasn't true, because I could increase P2 a bit, and then I'd find that this thing was still summable, and I'd get that the norm was still finite, but it was supposed to be infinite. Okay, so this inequality plus some elementary analysis gives you this inequality. Okay. Now, another really nice thing that happens is that when we want to control the 2 to 2 norm, we can use Cheeger's inequality. So the idea here is, suppose I take this matrix of connection probabilities and I divide by the susceptibility. Well, if I do that, I've obtained a stochastic matrix. I've obtained the transition matrix of some Markov chain, right? Because I've just normalized so that all the row sums and column sums are 1. So it's bistochastic and symmetric. Okay. So, and in fact, the way you can think about this random walk is that at each step you sample a size-biased percolation cluster where you are and move to a uniform point in the cluster that you reveal, and you just do it independently at every step, so it's a Markov chain. Okay. Now, there's a very nice way of estimating these operator norms of Markov operators. So if you have a symmetric stochastic matrix, you can define its Cheeger constant via this formula. So it's exactly analogous to how we defined the Cheeger constant of a graph before. That was just the Cheeger constant of the random walk matrix on the graph. Okay, and Cheeger's inequality says that, okay, so there's bounds from both sides, but I'm only going to be interested in the upper bound, that I can bound the operator norm by the square root of 1 minus the Cheeger constant squared. So in particular, the main takeaway is that this operator norm being small is equivalent to the Cheeger constant being close to 1. Okay. So in particular, if I apply Cheeger's inequality to this normalized operator, I get this inequality, that the 2 to 2 norm is bounded by the 1 to 1 norm, which is just the expected cluster size, times this square root of 1 minus this Cheeger constant squared. So this gives you a really nice criterion to prove that PC is less than P2. So in particular, if I can prove that the susceptibility diverges in the way I expect, the mean field way, where if I'm epsilon away from PC, it's of order 1 over epsilon, and I can prove that this thing goes to 0, i.e. the Cheeger constant goes to 1, then I'm done. Then PC is less than P2 too. And this is a really nice thing because this thing about the susceptibility, we very strongly believe this to be true in the non-amenable case. Right? It's one of these mean field exponents. It should already hold in Z7. It's certainly going to hold for tree times Z7. Right? And then this, I just have to show that it goes to 0. I don't have to show anything about the rate that it goes to 0 or anything like that, where it, once I know this, I can come back and say that this goes to 0 at least like PC minus P, but I just have to show any going to 0 at all. So I really only have to, I can take this mean field exponent plus an epsilon of extra information, I'm done. And this is really super helpful. So, and this criterion is what I use in the hyperbolic case to prove that PC is less than P22. Okay. So how much time do I have left? Oh, yeah. Okay. Okay. So rather than telling you more about this hyperbolic proof, because it uses quite a lot of hyperbolic geometry, and I'm not sure how familiar everyone is, instead I'd like to tell you more about these strong consequences of this PC less than P22 conjecture. They really gives you really, really nice results that I don't know how to prove any other way. So, for example, one thing is that you can get exponential decay of the connectivity probabilities at PC. So this is another one of these things that we sort of generally conjectured before for non-amenable groups. We didn't know how to prove it, that falls under this umbrella of consequences of the new conjecture. So if PC is less than P22, well, in fact, for any P that's smaller than P22, I can prove that the probability that U is connected to V is exponentially small in the distance between U and V. And I'll show you the proof of this shortly. And in fact, you can just think of this result. It's just an L2 version of the classical fact that if you have finite susceptibility, then you get something like this. And in fact, the proof is basically the same. I mean, you basically do the same thing, but with the operator norms instead of the first moments. So another instance where you can treat these operator norms very similar way to how you would normally use first moments in percolation. Okay, and in fact, the proof will also yield something I call cluster ballasticity for all percolation below P22. So what this means is that if I look at my percolation cluster and I look at two vertices, then it's the distance between them in the percolated graph is very, very likely to be of the same order as in the ambient graph. So I don't have these long snaking paths. This has some nice applications to exponents that I'll come back to in a second. And in fact, the way you prove all of these things is very simple. So it just comes down to the following inequality. So what I'm going to do is I'm going to look at the matrix CPN. So it's going to be, the entry is going to be the probability that U and V are connected and that their intrinsic distance, i.e. the distance inside the percolation, is at least n. And what I show is that if this 2 to 2 norm of the entire two-point matrix is finite, then the norms of these matrices have to decay exponentially. And in fact, you can get some explicit rate in terms of the norm. And this sort of immediately implies that the two-point function is decaying exponentially in the distance, but it's actually much stronger. So let me just show you a proof of this quickly. It's very simple. So I wrote down these definitions, but I'm not going to use these ones, so let's ignore them. So let's say I also introduce this extra matrix SPN, which is just like CPN. C stands for complement, this stands for sphere. So in SPN, I'm going to require the distance to be exactly equal to n rather than greater than or equal to n. Okay? And now I can write down an inequality that CPN is bounded entry-wise by the product of TP and SPN. Right? And this is a completely elementary thing. It's just that, I want to find the guys that are outside my intrinsic ball of radius n. So I can first explore the intrinsic ball of radius n, and then anything that's in this complement I have to connect to off of what I've already explored, which is harder than just doing it in the full graph. So if you formalize that argument with these matrices, you exactly just get this inequality, right? Where this is finding the guys at distance n and then going further. Okay. Now, in particular, but I also have that if r is less than n, then Cpn is smaller than Cpr, right, just trivially. So I also have that Cpn is smaller than Tp SPR for all r less than or equal to n. Okay? So if I look at Cpk plus 1 times n, then, well, I can bound it by this for every r between kn and k plus 1n, so therefore I can also bound it by averaging all those bounds. So I get 1 over n plus 1 Tp times the sum r from kn to k plus 1n of SPR. Right, but this I can just bound by Cpkn. Okay, so if I take norms here, I get that the norm of this matrix is bounded by the norm of this over n plus 1 times the norm of the previous one, Cpkn. Right? So if I just take n larger than this, then I can just iterate this bound inductively to get the exponential decay of these norms. And if you choose how to do this optimally, you end up with this bound. Okay, so this is a really useful thing. So as I said, it gives you this, what I call cluster ballasticity. It says that you cannot have a cluster that sort of goes far away and comes back and folds in on itself, where you end up with the intrinsic distances are much larger than the extrinsic distances. So because these guys are decaying exponentially, and the volume of balls in the graph are only growing exponentially, so it's a competing exponentials sort of thing. So it really tells you can't have these shriveled up long paths in small volume. Okay. And one consequence of this that I really like is that you can get the exponent for the extrinsic radius of an infinite cluster at PC. So this is just, I have the origin, and I look at the furthest point away that I'm connected to at PC. Right? So we can get that this is of order 1 over n, which is exactly what you'd expect for a critical branching process in a nonamenable graph. And the thing about this this radius exponent is it's typically a lot more subtle than the other exponents because it depends on the graph. I mean, even if you have mean field behavior, it depends on the graph just because the branching random walk exponent depends on the graph. Whereas if I look at the intrinsic radius, if I look at the probability that if I look at the cluster just as a subgraph, then it has diameter at least n, that's always of order 1 over n. So that was proven by, or under the triangle condition, it's order 1 over n. That was proven by Cosma and Nachnius. But the extrinsic is more complicated because in the non-amenable case, you expect this to happen because a random walk will go distance n in n steps. Whereas in ZD, the random walk only goes distance root n in n steps, so the exponent will be different. You actually get n to the minus 2 here for the exponent in ZD in high dimensions. And, but once you have this cluster ballisticity thing, you just can read this off from the intrinsic one. Because if the intrinsic guy gets to distance n, then it just, with overwhelmingly high probability, it's your extrinsic distance order n as well. Okay. And I guess I have a minute to tell you one more thing. So another very strong consequence of this PC less than P22 thing that I also like is the following. So suppose I look at the Q to Q norms, right, of the critical matrix. So I know that, so if PC is less than P22, it means that the one-to-one norm, that's always infinite at PC, or the infinity to infinity norm, there's duality, right? But I can look at other values of Q in between. And in fact, you can compute what the exponent's describing the way these norms diverge as you approach these boundary values of 1 and infinity are. So in particular, if I take the take this 2-point matrix and I look at the Q to Q norm where Q is very large, then it's of order Q, the norm. And similarly, I can look at things about how different PQ to Q is from PC. So one thing that you can do with this, so this is really an extremely strong estimate. It's a bit of a weird estimate if you're not used to using these operator norms, but it's very strong. So in particular, one immediate consequence of this is if I take critical percolation and I look at any fixed set of vertices in the graph, and I say, what's the expected size of the intersection of the cluster at the origin with this set, then it's always bounded by log of the volume of the set. So this is one cute thing. Another thing you can do with this is you can look at the Hausdorff dimensions of sets of boundary points. So, for example, imagine I have percolation in the hyperbolic plane. And I look at I'm at some value of P between PC and PU. So if I look at the cluster at the origin, it's infinite. It accumulates to some random set of points in the boundary of the hyperbolic plane. Right? And let's say I look at the Hausdorff dimension of this set of points. So it's delta P. So it was proven by Steve Lally that delta P is a continuous function of P in the two-dimensional case. So it starts, well, it's 0 below PC, and then it sort of goes up to 1 at PU and then stays at 1. So one thing that you can do with this result that I don't think it was known how to do before is you can look at the exponent here. So if I go to PC plus epsilon, how does the Hausdorff dimension of this limit set depend on epsilon? So it's actually very easy once you have this to show that it really is order epsilon. And the same thing works in higher dimensions as well. If I look at the dimension of this limit set at PC plus epsilon, it's order epsilon. I should say, in fact, you can also compute this exponent, but not using this, using older things, but it hadn't been done before. So it turns out that if you're at PU minus epsilon in one of these tessellations of the hyperbolic plane, then the Hausdorff dimension of the boundary is order 1 minus epsilon squared. And just to mention one very nice and I think extremely hard open problem to give everyone some homework. So imagine I do this in high dimensional hyperbolic space. Okay, so what I believe happens, but I have very little idea of how to prove this, is that the following. So rather than continuously going from 0 to 1, it should do the following. So we'll start off linearly, like this, but then it should have a sort of cusp here where the derivative blows up at pu, and then a jump discontinuity. And the reason I believe this is that branching random walk does the same thing, and we sort of expect that once you're in high dimensions, branching random walk and percolation should have similar behavior. But this is an extremely interesting problem, I think, and it seems extremely hard to approach with current methods. Anyway, thank you.
One silly question. What is the analog of PU for branching random walks?
It's the recurrence transience transition. So branching random walk, first it will start surviving, but the origin won't be visited infinitely often, and then once you get to 1 over the spectral radius, it starts visiting the origin infinitely often. And this picture was actually proven by Lally and Selke, I think, that it has this jump discontinuity, and you can say what this exponent here is describing how the derivative blows up and so on.
Okay, let's thank them again.